So the paper we submitted with my colleagues Arno Stelling and Fabian Schur is called La Scène Musicale, a case study on design for manufacture and assembly. And the goal there was to explore the solutions specifically developed for this project and the way workshop, pre-assembly, and on-site constraints have been integrated in the parametric modeling process of this complex timber structure. The timber structure we are talking about is the one of the auditorium, as you can see here. It's located at the tip of the East Second Island. And this auditorium is part of a bigger cluster of rehearsal and representation space in place of the former Reno industrial plant. It was designed by Urban, as you might have noticed from the signature hexagon pattern on the facade, and fabricated by S Timber in Germany, with SGB as a timber engineer and us, design production, as digital planner. On every project, what we try to avoid is to solve problems as they come, because this will end up in endless loops and huge pile-up of hot fixes. And instead, we try to integrate material, engineering, fabrication, and assembly concerns from the very beginning of the process. But since we don't do engineering nor fabrication ourselves, we need to gather all the involved parties around the table to address these topics. What we do is that we translate a set of inputs from various sources, be it a surface, list of load cases, into small scripts that brings us a step closer from the final model. And since problems are anticipated from the previous phases, looping back to a previous stage should theoretically be unnecessary. On this project, the inputs consist of one reference surface and 99 axes that were provided by the architects. And since all the planning steps depend on these reference geometry, the first thing we do is that we ensure that the quality is good enough. So are the surface and axis continuous, or they're properly intersecting, where's the surface seam located, and so on. And once this is done, what we do is that we sort all these elements and we set up an ambiguous and comprehensive naming system for all of them. And then we go from the modeling, and the first thing we do there is that we extract the joint positions from the curve intersection, and we pass that to the engineer, which can then use that to create a structural model from the polynomial descending. And the structural model is used to define the cross-sections, to estimate the amount of detail types, and to identify the critical cases, both on a structural and geometrical point of view. And then we go on drawing the beams as volumes. And the cross-section of the beam in this project varies between the foot and the ridge, and this is due to the different structural requirements. And this is reflected by a variable offset of the reference surfaces that will be used to define the beam's horizontal levels. The beams are then created as an interpolation of intersection between the perpendicular frames and the axis and the master surfaces. And doing so, we ensure that all the edges intersect at the crossings, which is a critical condition for precise detailing and execution. And we also ensure that the beam's faces are root surface, which means they can be easily milled with a cylindrical tool. So in this respect, we already anticipate the detailation work and the fabrication. So in order to be shipped and fabricated, these beams need to be shortened to segments. And we have two different strategies there. The ring segmentation is defined by the transportation limitation. So the piece should not exceed 18 meters, because otherwise they would not fit in a regular truck. So the goal is to achieve an harmonious division within this 18-meter range while avoiding vertical alignment. This being said, some structurally critical segments can span up to 24 meters. And in this case, we do accept the logistical effort to keep the cross-section and detail complexity in an acceptable range. The diagonal segmentation there is defined by the assembly concept, and they span between two consecutive rings. So we end up with 1,162 different pieces, which at the end is more than 8.2 kilometers. And the timber structure is designed to be self-supporting from the very beginning of the erection process. So the levels are added horizontally one after the others, using very few punctual supports. which allows us to save the cost and space of the scaffolding, and that's always a good news when you're working on a narrow island, which is turned into a massive construction site. Additionally, the entire structure was mounted using the only available crane outside and during nighttime, since it was used at daytime for the concrete work. So the diagonal are pre-assembled into X shape before being shipped to the construction site. And they are mounted on existing ring from the outside. And doing so, the crossing between the ring and diagonals also act as a longitudinal joint at the end of every diagonal segment. Here you can see some of them before being shipped. And you can notice the chainsaw in the lower corner, which in this case is simply used as a luxury paperweight because there's no other need for it. The rings there are rotated into place from the outside around the longitudinal joints. And as the piece rotates, the lap joints on the ring successively makes contact with the diagonal. And this allows the assembly team to engage them one after the other. Yes. And since we need to know every assembly direction beforehand, these are stored in the model and later used for collision checking. So the first step in the fabrication process is to create blanks. These have been a bit introduced by the InnoChain team. So the blank is the raw piece of glue and keyboard that approximate the final shapes. And they are produced by bending and gluing raw lamellas on a set of pre-shaped supports. What we usually do is that we mix straight single curve and double curve blanks, depending on the final segment's curvature. Oh, thanks. Is it okay now? In order to optimize the cost. And the critical aspect is the fiber cutting angle, which has to stay below 5 degrees in order to keep the structural strength of the piece. But in this particular project, one of the requirements was to avoid visible cuts in glue gaps. And this means that you cannot mill the outer lamella, which you can see in white there. So at the end, the blank has to precisely fit the final piece. And the other size can be as small as 10 millimeters. Which, when you think about it, is pretty small for 24-meter long ring segments. And in order to precisely place this blank on the milling band, the clamping position were created in the model on both sides, top and bottom, and then exported along with the gluing data to be marked on the piece. Another trick for the blank is that concern the diagonals, and to assemble the crosses in cross shapes, the diagonal connection is designed as a lap joint, which means that one of the diagonal has to be split in two parts to be assembled around the other one. So to do so, we insert a dry lamella in the middle of the counterclockwise diagonal. And on this dry lamella, the glue is only applied at 3 specific spots, which are the both ends and the central lap joints. And when these details are milled on the CNC bed, the 2 parts separate from each other. And this way, we can use only one set of gluing and milling data, meaning we can spare a third of the global efforts. The only restriction then is that the blank middle axis has to exactly follow the piece middle axis, and that the lamella counts in heights must be an even number in order to place the dry lamella exactly in the middle of the piece. Here you can see some of the blank waiting to be milled, and on top of all of them, you can see the MDF templates with the clamping position for the CNC bed. In parallel, we start the detailation work, and these are done from 2D plans that we create along with the structural engineer. And in this case, the close collaboration with the engineer ensures that the details parametric implementation will be quite straightforward. Then these are instantiated on the corresponding joints, which are being prealably identified by the types. And in the same musical, we had 2,789 unique joints, which were grouped into 8 main types and then subdivided into 100 subtypes, which is quite a lot already because you have to implement all of them. And it's very important to resist the impulse to start with the simplest solution, even though they can cover up to 90% of the project. But when it's possible to start with a complex one, and to develop a parametric solution that also covers the simpler cases. So while we are instantiate the details, the required relations are created between the elements. And this means that the joint knows its segments and vice versa. So when we will export the fabrication data for a segment, it will query all of its joints and all of their fabrication operation. And the attributes we attach to the operation are then as important as the geometry definition itself. And they can cover various topics such as width and depth for a pocket, reference type and assembly number for a screw, and so on. And since a segment can connect multiple other segments at different points, there is not only one assembly direction that could fit all of them. So to address this, the side of the lap joints are slightly screwed, as you can see on the bottom. And since this is likely to weaken the cross-section of the piece, these screwing angles are extracted from structural model and individual for every joint. At the end, all the operations are placed in the model at the reference level, which means that there's no margin applied yet. And instead, these tolerances are stored as attributes on the piece in order to be individually tweaked following the feedback that we receive from the workshop and the construction site. On such project, the margin value usually navigates around 0.5 millimeter. This being done, the fabrication operation are translated into BTL format and passed to the fabricator to be milled. Here you see some of the piece being post-processes. These include cleanings and pre-assembly of all the required fastening elements, so screws, steel pieces, bolts, so on. And here are the ring pieces. You can see the hardwood detail that have been explained more in detail by my colleague at the last Fabricate conference. And in order to ease the post-process and the quality control, what we do is that we export individual plan drawing for all of these pieces, and this plan displays the control measurement and clamping position along with all the embedded details. This was for the simu, but on the more recent projects, we went as far as displaying all the individual screws and steel pieces for every different joint on such plans. Once this is done and the piece is fabricated, they are shipped in site. For the story, the diagonal crosses that you can see on the picture, these were stored on the canal barge stationed along the Seine, which during heavy rain in the winter became temporarily out of access. But luckily, this did not result into much delay as the assembly process was pretty smooth. Here is the first ring being assembled. You can notice the punctual supports I was talking about earlier. And you can also see on the bottom of the wood pieces the steel details. And these were one of the most complex ones to develop since it combined both heavy load bearing and extremely diverse geometrical configurations. To support the team on site, what we send them is exported montage plan that are exported for every ring levels. And this features the name of all the joints there along with every segment. And at the very end of the construction process, we reached the upper concrete ring, which is located 27 meters higher than the floor level. I told you earlier that we did not need any scaffolding. Also, you can see one here, and this one was actually used by the facade team to place the facade elements on site, which did not make the structural engineer very happy because this was not calculated for it. And this actually reflects the fact that we had very few contact with the facade team. Amongst more other things, we only received information about the lower face of the facade cluster because we had to pre-drill some screws there on the transition wooden pieces on top of the segments. And this stresses out the importance of bringing all the involved parties around the table and to anticipate the fabrication and assembly early enough in the process. Only then can we achieve such ambitious and precise results. Thank you for your attention.